Okay, so we are live, and next day of our neetcode challenge for 60 days. Today is day 11. So what I can tell you. So I checked how it should be done, and the logic is the following. So we should have a prefix map, and we should iterate over our array, and then to check each of our possible subarrays. And to collect possible subarrays, we put all these possible subarrays in this prefix map. So at the beginning, we have, so for example, we have some array, right? At the beginning, we put that we meet sum of 0 one time, right? Yeah. And then we have prefix sum. And at the beginning, it would be 0, right? Then we add 1. And we calculate our k minus 1, right? K minus, so 1, it would be 0, right? It's k is equal, so in our case, k is equal to 2, right? And we have this array. So we have prefix sum, that it's this one, and then we have current sum. And current sum is 1, because we, for example, we are on this position. And we check k minus current sum. It's equal 1, and we don't have such value in our map. So we just add our current sum as 1 that we meet one time, right? Then we go here. Our current sum becomes 2. And k2 minus 2, it would be 0. And we see that we meet 0 one time. So let's say that we have our result that we increment by 1. And we also put 2 that we meet one time. Okay, and then our current sum becomes 3. And 3 minus 2, it would be 1. So we see that we 1 already have, because we need to calculate all these two values. And we put 3, 1, and also increment our result to 2 and return the result. So let's try to implement this. So we have our result as 0, and then we have our prefix sum map, integer to integer, map. Then we iterate over our array. And we calculate, we should have current sum, that is 0, and current sum plus nums I. And here in map, we should put map, put 0, 1. And here we can check if map contains k minus current sum. So if it contains, then we can increment our result to map get k minus current sum. Okay. And here we can put this value by current sum. We put map get current sum equal now 0, otherwise plus 1. Yep. And we return our result. So let's check. Let's understand why it doesn't work. Current sum, so we put it. Map contains key, k minus current sum, k minus current sum. So we have 0 and 1, right? Then, so yeah, so let's take this an example of our array. And yeah, so have this one, so we iterate. Our map would be 0, 1. Then our result is equal to 0. And our current sum is equal to 0. Then we iterate. So we put first a value here. And we check that it doesn't contain. So we just put 1 equal to 1. Because we take current sum. And current sum is 1. And here it will be null. Yeah, so if it's null, we put 1. Otherwise, we put like this. Yeah, so I think it should work. No, okay. So if current sum is null, so we just put 1 here. So it would be 1, 1. Then we go to the next one. And current sum becomes 2, right? And now 2 minus 1. 2 minus 1, it exists because it's 0. So we just put 1 into our result and go out from the 3. And here we have 2. So we just put 2 as equal to 1. Then we go to the next one. It becomes 3. So 3 minus 2. 3 minus 2 exists. Yeah, because k. Okay. So it's 2 minus 3. So it's minus 1. So that's why we didn't put it. We didn't put it. What if we remove current sum minus key? Otherwise, I think here should work. Yes, and then submit. Yeah, and we see that currently it works. Let's check other. Yeah, so we have the same current sum minus key. Yeah. So yeah, so the following is the logic, like, so we collect into prefix map and iterate over our array and check if it contains and to return our results. Okay, so we're done. And the final boss and the final task here in array and hashing topic. First, missing positive. So let's take a look at this boss. So it's hard problem, and to tackle hard problems, we need to do the whole list of our flow. So first, understand. Second, it depends actually on the task. So if we didn't understand fully, we need some test cases. Then to think about constraints, because it depends. What algorithm will select depends on the constraints. Also, before, after understand, maybe it's optional to have a definition of our task. and then to investigate approaches that we have here, then time space complexity for the selected approach, and also for each of the approaches. And after only after this, we go to implementation. We should do it quite fast. And after implementation, we do a dry run and do refactoring if it's needed. So here we have like 6, 7, 8, 9 positions. So first, let's understand the problem. We are given an unsorted array. Return the smallest positive integer that is not present in nums in this array. So not sorted array and the smallest positive integer that is not present in nums. And you must implement an algorithm that runs linear time and doesn't use any additional space. So that's important. So we have unsorted array. So let's just bring some array here. And our task is to return the minimum positive integer that is not present. So minimum positive, it's actually 3, because otherwise it would mean negative, correct? If we have, like, do we have empty array? I think no. So, for example, if we have 1, can we calculate like positive integer as 0? As 0? Probably no, because it's not positive, so it should be 2. So from here, like 3, 4, minus 1, 1, the smallest positive integer is 2. Yes. And we also can have like a lot of different integers, and we have like 9, 1, 2, 3, like 8, 4, 5, 6, then minus 10. Actually, we are doesn't care about negatives, and they are not sorted. So 1, 2, 3, 4, 5, 6, 7. Yeah, and we see that it can be like a very big number of values, and definition we actually don't need here. So with understanding this one is our test cases. And the third one is constraints. So I would probably ask, so here it's the result is 10. I would ask about the length. So let's say if we need linear, so let's say that it's quite big one. So it's from 1 to 10 minus 7, correct? It's minus 5. But, and also array lengths can be any integer. So it's whole constraints. So now let's think about approaches. So if it's linear, because if it's not linear time, then we definitely can sort and search by binary search or even without binary search. So we can just sort this array and go one by one and just find the positive. What other things, like we can iterate, we can like store in map and just iterate it. So so definitely if it's not sorted, we need some prefix sums, I believe, here. So to understand prefix, so let's first understand prefix sum, what we can have here. So with prefix sum, we have 2, and then 3, then 3, right? So with prefix sum is definitely is going by incrementation. And maybe if we go by incrementation, what we can do, it's actually, for example, here we have a scale from 1, 2, 3, and so on. And here we have a scale of how many numbers we can have here. So it's kind of a function. So, so by 1, we increment by 2, right? So when it's 1, or maybe we can do like this. So when it's 1, it's 2, right? Then we increment, when it's 2, is 3, right? So here incrementation is greater than this one, and we can check the difference between all these incrementations, and we can check, find the minimum differences between them. And we can say like 1, right? So I expect that my value, or let's say no, let's say that I expect that my minimum is a max positive integer, so from 1 to some 2000. So let's say it's like max integer here, so it's my minimum. Then I go here, I can check incrementation between 2, so from 0 to I have incrementation to 2. So when it's decrementation, I probably should not check this. And in this case, it's actually we find the minimum here, but what it gives to us. So we find minimum. Actually, nothing gives to us, right? Because here, then it go to 2, then it go to 1, and 1 is already minimum. Minimum, it even can like be negative. So yeah, so it doesn't give us much, because here we have, like in this example, we have 1, 2, and 0. Maybe I should find the maximum. Or maybe minimum and maximum. So and let's say that maximum integer and minimum is 0. So when I increment here, I can check. Yeah, I can check. I can move the maximum to 2. Now here it's like 1. So I can move maximum to 2, then 1. Yeah, and it's 1 again. Oh no, so it definitely does not work here. What about this one? So I have 3, so 3, then 7, then 6, then 7. How I can calculate 2 here? Yeah, I don't know. Yeah, it's really hard. It's really hard here, because I even don't know how to tackle this challenge. I don't know how to tackle this challenge. Yeah, so I need some hint here. So let's think. So let's imagine that we are in a real interview and we hear the first hint. Think about how you would solve the problem in non-constant space. can you apply the logic to the existing space, non-constant? Okay, so if we need non-constant, I believe, as I told, so we can put this into the map, all these values, and then iterate from 0, like from 1 to maximum integer, and try to find the positive integer value here, or even like not map but just to set. So we put all positive integers positive, so negative we just miss, all positive integer into set, and find the first positive. Okay, what if then we don't have set? And what if I said that minimum is 1? Minimum is 1, and when I meet some 1, I can tell, yes, so this one is not giving me any much. We don't care about duplicates or non-positive integer. Yes, so that's definitely something about set. And here, remember that 2n is equal to n. Okay. So what does it gives to us? 2n is equal to n. Okay, so maybe we can, at least we can make this okay, so maybe we can modify our map somehow. So when we meet integer 1, it looks like a certain, but no. Okay, yeah, so I know how to solve this with memory. So with memory, it just, as I said, like it's new hash set. So it's very simple. So let's solve it with memory first and understand. So we just iterate over our nums. We just add num to set, and then we just iterate from 1 to a integer max value, a plus plus, and we even can do this, yeah, in binary search, I believe. So yeah, and here we can check like if if set contains I false, then we just return return I, otherwise we return -1, something like this. So it's 4 lines of code, and if we will submit, it should pass. So, but yeah, it's, as we see, it's super not efficient. So I believe here we should have something. I don't, this hint is not enough for me. So something it's working better here. Boolean, yeah. So it's, for me, it looks the same. In my previous submission, it looks the same. Yeah. It's faster, but for me, it looks the same. We have nums. We have iterations from 0 to n, okay. And here we had iteration, so while is greater than 0 and yeah, so it looks like this one looks like not linear. Okay. So we left and okay. Do we have, yeah, we have editor, okay. So the task is to find the smallest positive integer, that is not present in nums. Know that positive are greater than 0, okay. Let's discuss two main cases. No missing integers, okay. So mass contains 9 elements, the smallest missing is 10, yes. For an array of length n, if the array contains all integers, n, the smallest missing positive integer. Okay, yeah, makes sense. Missing number integer here. Its num contains 9. I think 5, yes. For an array of length n, if the array doesn't contain 1 to n. Okay. So let's also discuss the constraint. Time complexity. Hint number 3 reminds us of this one. While we know that 1 does not equal 2. All notation describes the algorithm's limiting behavior as the input size grows towards infinity. Okay. The optimized approaches in this article use in-place solutions. Does in-place mean a constant space complexity? By definition, an in-place algorithm transforms the input using auxiliary data structure. The problem-specific ask. Okay, so Boolean array. We can solve the problem by iterating through the number 1 to n and use linear search to determine whether each number is in the array the first number cannot find. Okay, so we initialize array, make the elements from nums in the lookup array. So if greater, we put this in. So it looks like a set here. Yeah, for me it looks like a set. Okay. Index hash key. So for me, so this one is the same as we see. So space is still n. Cycle sort. In the first approach, we discussed that we can solve the problem by iterating through the numbers 1 to n and searching for each in the array. If nums were sorted, the search process could be done linear time. Okay, so it looks like the same approach. So we put 10 here, so we sort, okay. So let's check. Use cycle sort to place positive elements smaller than n at the correct indexes. Okay, so have swap, correct index, swap, so it's just simple iteration, and here if it's greater than 0 and less than n and not correct index, we do this swap operation. So this minus 10 is actually minus 10 is not greater than, so we just pass this minus 10. Yeah, so we pass minus 10, then we have 1. 1 is greater than 0, it's less than n, and correct index 0, so no, it's not correct index. And correct index, do we implement like correct? So we just do here swap. And correct index would be 0. Okay. So we are telling that this should be at correct index. So we just swap these two values by I. Okay, makes sense. Then 2 swap. What about this 2? Swap with this one. Swap with this one. Swap with this one. Okay, and then we iterate one more time, right? Yeah, we iterate one more time and it'll be fine. Okay. Yeah, so pretty interesting problem. I think it's more not hard, but it's like kind of intuition, but I believe this one's also quite good. So we can just put it as done. And we are finished with array hashing for today. And we see that we left with all these topics, but we finished with the main one. And it's a good starting point here. And see you the next day.